This video is brought to you by mywayteaching.com.
So, in this part, we are going to study about the concept of potential energy. See, whenever we heard a word potential, it reminds us of possibility, or we can say capacity for any action, isn't it? The term potential energy brings to one's mind the stored energy. Potential energy is nothing but stored energy, isn't it? A stretched bow string possesses potential energy. When it is released, the arrow flies off at a greater speed, isn't it? So, that is because of potential energy. Another example, like the Earth's crust, it is not uniform, isn't it? And it has discontinuous as well as dislocations that are called as fault lines, and these fault lines in this earth crust are like compressed springs, okay, which means they have potential energy. So they possess not only a limited, a large amount of potential energy. An earthquake results when these fault lines readjust. Thus, potential energy is nothing but the stored energy by virtue of the position. Kinetic energy is the energy by the virtue of its motion, whereas potential energy is nothing but the stored energy by virtue of its position. Okay. See, the body left to itself releases this stored energy in the form of kinetic energy. So let us understand it in more detail. The gravitational force on a ball of mass m is mg, isn't it? The gravitational force on a ball of mass m is given by mg, isn't it? Where g may be treated as a constant near the earth's surface. By near, we imply that the height h of the ball above the earth's surface is very small compared to radius. Okay, if we say g is near the surface of the earth, then we must consider that the height above the earth where that ball is located is very much smaller compared to the radius of the earth, so that we can ignore the variation of g near the earth's surface. So we will take the upward direction as positive and downward direction as negative. So let us raise the ball up to a height h. So the work done by the external agency against this gravitational force is given by mgh. Okay, the work done by the external agency, that is given by mgh. Okay, So this work gets stored as potential energy, and the gravitational potential energy of an object as a function of height h, it is denoted by v of h. Okay, so we can write this is the gravitational potential energy, that is the work done by the external energy on a ball. So we can represent it using notation, that is v of h, that is equal to mgh. Okay, so if h is taken as a variable, it is easily seen that the gravitational force F is equals the negative of derivative of V of h. Okay, if if you consider h as a variable, then we can say the gravitational force F so is equals to the negative of variation of, or we can say the derivative of V of h. Okay, we can write it as minus mg. So the negative sign indicates that the gravitational force is downward. So when released, the ball comes down with an increasing speed, isn't it? Just before it hits the ground. So its speed is given by the kinematic equation, means when that ball is dropped towards the earth, it moves with certain speed, isn't it? And that speed is given with the kinematic relation. We will call it as kinematic relation. So that is given by v square is equal to 2gh. Okay, kinematic relation, and this equation can be written as half mv square is equal to mgh. Okay, so which shows that the gravitational potential energy of the object at a height h where the object is released manifests itself as kinetic energy of the object on reaching the ground. Okay, the potential energy at a height h, it will manifest itself as kinetic energy when it reaches the ground. Physically, the notion of potential energy is applicable only to the class of forces where work done against the force gets stored up as energy. When external constraints are removed, it manifests itself as kinetic energy. Okay, the potential energy V of x is defined if the force F of x can be written as minus dv by dx. Okay, so this implies that we can write it as xi to xf, isn't it? The variation f of x dx is given by minus of vi to vf dv. So this one is given as vi minus vf. So the work done by the conservative force such as gravity, it depends on the both initial as well as final positions only. It depends on initial as well as final positions. If an object of mass m is released from rest from the top of a smooth inclined plane, say of height h, then its speed at a random bottom is given by square root of 2gh. If object of mass m, okay, if it is released from rest, okay, if it is released from rest from the top of the smooth inclined plane of height h, okay, of height h, then its speed at the bottom is given by, so this inclination, that is the speed at the bottom, is square root of 2gh. It is irrespective of the inclination. Thus at the bottom of the inclined plane it acquires kinetic energy, that is given by mgh. Okay. If the work done or the kinetic energy did depend on other factors such as velocity or the particular path taken by the object, then we call that force as non-conservative. Okay, if the kinetic energy depend on the velocity or the path, then we call those type of the force as non-conservative force. Okay. See, the dimensions of potential energy are, that is given by m L square T raised to minus 2. So, and the unit is joule. Okay, unit is joule. So, the same as kinetic energy, or we can say work. So, to reiterate, the change in potential energy for a conservative force delta V is equal to the negative of the work done by the force. Okay, the change in potential energy, that we can write it as delta V is equal to the, okay, it is equal to the negative of the work done. Okay, negative of the work done by the force. So the change in kinetic energy, we can write it as the negative of the work done by the force, that is minus of f of x into delta x. Okay. So, in the example of the falling ball which we considered, so we saw how potential energy was converted into kinetic energy. So, this gives an introduction, or it is the base for the principle of conservation in mechanics. Okay, so about this principle of conservation in mechanics we'll study in the next part. So in this particular part we saw how the potential energy is converted to kinetic energy, isn't it? And even at the bottom of the inclined plane, how it works and what is the speed at the bottom. We studied about all those things. So in the next part, let us study about the conservation of mechanical energy.